Hello, my name is Farah Mangley. I'm a sophomore at BOROUGH Community College. I'm also a CRSP research student. I would like to thank my professor Abel Navarro for his support and direction in assisting me to finish this program. My focus today is Gold 3 uptake on brown marine algae. These are some of the outlines that we'll discuss today. These are the chemical structures of main polysaccharides in brown marine algae: the polygenic acid and the fuchsidin. Lawsonia, Sagressums, and Sagacium borae S12 and L13. These absorbents were tested for the ability to absorb gold-3 ions from aqueous solutions on two different types of Proverian brown algae. The initial pH, gold ion concentration, and absorbent dosage, particle size, and salinity of both algae were investigated. Furthermore, the absorbent's instrumental characterization shows that these materials have a high potential for green recovery of gold-3 and other precious ions from contaminated wastewaters. Brown marine algae are also well known for biomass for bioabsorption because they have showed high methyl absorption capabilities and also fungus, yeast, and other dead biomass. These are the materials that were used: the brown marine algae, Sinonia, Sagressium borae L13, and Sargassium modosum borae S12. Gold 3 chloride, deionized water, 0.1 HCl and 0.1 sodium hydroxide for pH adjustments. Atomic absorption, spectrophotometer, Perkins-Elmer 3110, and sodium nitrate for a salinity effect. These are some of the pictures of the materials. These are some of the methods that were used. The results for the pH effect of the initial pH on the absorption of gold 3 onto L13 and S12. These concepts can be explained the result in figure 1. Even though L13 and S12 are brown marine algae, they have different absorption capabilities and pH behaviors with other contaminants. S12, for example, has a strong attraction for positively charged ions like lead and copper, whereas L13 has a greater attraction for stronger deactivated phenolic compounds, 2-nitrophenol. As a result, L13 should have a greater affinity for gold chloride 4 than S12, which is more consistent with positive particles. At lower pH levels, both algae have a low absorption capacity due to their negative charge, carboxylate, and are likely to be absorption site for gold-3 ions. And even when protonated neutral form, the high electron density would repel the gold ions. As a result, the pH effect would be completely reliant on the aqueous chemistry of the absorbate. At pH 5.0, L13 absorption increases linearly, whereas L12 absorption declines. The structural difference between L13 and S12 could explain this tendency. Figure 2 showing the results of the effect of the absorbent dosage on absorption of gold-3 onto L13 and S12. The goal of this experiment was to determine the maximum absorbent mass that saturates the absorption site on the surface of the algae. This assay is an important parameter for future studies on scaling up processes and continuous flow experiments. In figure 2, it depicts the differences in absorption capacity of both algae at various masses. There are no significant changes in absorption after 7.5 milligrams of L13 as observed. S12, on the other hand, exhibits a more linear absorbent dosage dependence. As a result, adding more absorbent will not improve the processes. Figure 2 also shows that a higher absorbent dosage, the absorption capacity decreased after reaching a minimum platinum, Q50 and 32 milligrams or grams of L13 and S12 respectively. This phenomenon has been observed in the absorption of phenolic compounds with marine algae, which is due to partial aggregation of the algae in solution, which reduces the number of available absorption sites. 3 showing the effects of the ionic strength on the absorption of gold ions onto brown marine algae in L13 and S12. Although metal-containing wastewaters from mines and industries are composed of both organic and inorganic substances, there are few studies that look at ionic strength as a factor in metal absorption. The absorption mechanisms is related to various types of electrostatic interactions, complexation, ionic exchange, electrostatic forces, etc. Between the absorbent and the absorbate, these attractions are strongly dependent on the electrostatic environment of the system, which can be determined whether the interaction exists. Other ions in the solution usually pose strong competition for metal absorption sites. Figure 3 depicts effects on the ionic strength, which was expressed in the experiment as a sodium nitrate as a model salt in the solution. The results show that the presence of sodium and nitrate ions strongly affect the interaction between the trivalent ionic ion and the adsorbent. In contrast, the most absorption studies that report a negative effect of ionic strength on absorption. Absorption was increased for L13 by approximately 35%, as you can see on the graph, and maintain almost constant value of S12 at increasing salt concentrations. These phenomenon could be explained by nitrate ions shielding the allogeneic group. As previously stated, negatively charged allogeneic groups interfere with the absorption of negative gold ions via electrostatic repulsion. By shielding these groups, their negative effect is reduced and absorption is increased. Perhaps S12 does not have the same effect because of its more egg box model shaped structure. The more linear and extended structure of L13 facilitates the approach of nitrate ions to allogeneic groups, avoiding negatively charged repulsion at the absorbent or per absorbate interface. Because of their chemical properties as a spectator ion in solution, sodium ions have no negative effect. The third results would be shown in figure 3, the absorption isotherms of gold ions on brown marine algae L13 and S12. Atomic absorption flame spectrometer was used to determine the amount of gold absorbed on brown marine algae in the resulting liquid. The isothermal plots at a room temperature between the absorption capacity of L13 and S12 algae and the remaining concentration of gold ions, which is gold 3 ions, in aqueous phase. The obtained results were also adjusted to the DR isotherm to determine whether absorption occurs through chemical or physical processes. The linear coagulation coefficient must be within acceptable limits for this purpose. For L13 and S12, the R2 values were 0.996 and 0.947, around the limit of 10, respectively. The magnitude of the parameters E, mean absorption energy, is important because it indicates a type of bioabsorption processes, such as chemical ions exchange or physical bioabsorption. The E value ranges from 230 to 320 joule per mole, indicating the weaker physical forces involved in the absorption of the gold 3 ions on brown marine algae. Van der Waals forces could be among these. These results were expected because using negatively charged absorbents has a high electrostatic penalty. The absorption of gold 3 ions by L13 and S12 is better compared to earlier studies involving green marine algae, Chlorella vulgaris, rice hucks, and activated carbon. Under the same experiment conditions, these absorbents reported mass absorption capacity of 22.13, 39.84, and 76.92 milligrams per gram, respectively, which we were surprised because of how small amounts we find. Shown on the left-hand corner of the screen, the two equations that were used to calculate the absorption of the brown marine algae, S12 and L13. And on the right-hand side of the screen shows the value of the two brown marine algae, of the Qmax value of 224.22 for L13 and S12 will be 59.311. Figure 1 and 2 show an instrumental analysis of the observant by electron microscope and energy dispersive X-ray spectroscopy. On the left hand shows 3 times 3000, and on the right hand shows a times 500. These are two of the other figures for L13. For the EDX images, on the left hand shows a times 800, and on the right hand shows a times 1000. To conclude, we discovered that L13 has the maximum absorption capacity. There's no morphological difference between the L13 and S12. It's only the composition that were contained from different polysaccharides. We also discovered that brown marine algae have special components like copper, lead, and even other organic compounds. Again, I would like to thank Professor Abel Navarro and the Science Department of BMCC, and also CUNY Research for this opportunity. This was my poster that was created from the experiment. Everything is included here. Thank you for your patience and for allowing me to present them today. Thank you.